In this lecture, we are going to derive a well-known fact regarding the convergence rate of the Newton-Raphson method, or simply Newton's method. The Newton-Raphson method, or Newton's method, is a numerical technique for finding solutions to the equation f of x equals 0. For this lecture, we suppose that f of r equals 0 and that we are approximating the root x equals r. We assume that f is differentiable up to arbitrary order and that f prime is not equal to 0. To begin the derivation, we start with the recursion formula of the Newton-Raphson method. If a sub n is the starting estimate for x equals r, and a sub n plus 1 is the next estimate, then a sub n plus 1 equals a sub n minus f of a sub n divided by f prime of a sub n for all values of n. We can treat the right side of the recursion as g of a sub n, so that a sub n plus 1 equals g of a sub n, and we have a fixed point method or Picard method thingy going on here, where the equation x equals g of x takes the place of the equation f of x equals 0. G of x equals x minus f of x divided by f prime of x. We plug in r for x in this equation. F of r, of course, is 0. And so we get g of r equals r, and that x equals r is a true fixed point of g. When applying the fixed point method or the Picard method when approximating x equals r, having the absolute value of g prime of r less than 1 and g prime continuous guarantees the convergence of the method if we choose our starting estimate a sub 1 close enough to r. Let's examine g prime of x. From the formulation of g, the viewer can check, as a differentiation exercise, that g prime of x equals f of x times f double prime of x divided by the square of f prime of x. We can see from this last equation that f prime should be non-zero. In addition, having f twice continuously differentiable will make g prime continuous. We plug in r for x. And so g prime of r equals f of r times f double prime of r divided by the square of f prime of r. X equals r is supposed to be a root of the equation f of x equals 0. And so f of r equals 0, making g prime of r equal to 0, whose absolute value, of course, is less than 1. Therefore, the fixed point method, and hence the Newton-Raphson method, should have the sequence of estimates a sub n converge to r, provided that the initial estimate a sub 1 is close enough to r. To determine the convergence rate of the Newton-Raphson method, we expand g of a sub n using a Taylor series around x equals r. G of a sub n equals g of r plus g prime of r times the quantity a sub n minus r plus 0.5 g double prime of r times the square of a sub n minus r. And then we have the third degree error term g triple prime of c divided by 6 times the cube of a sub n minus r. The real number c is some value between a sub n and r. A sub n plus 1 is g of a sub n. Since r is a fixed point of g, g of r is r. G prime of r is 0. Now we define the error value e sub n to be equal to a sub n minus r. Since a sub n converges to r, we assume that e sub n is already quite small and that e sub n cubed is even smaller. so we can disregard the third-order error term provided G triple prime is bounded. We subtract r from both sides. On the left side, we get a sub n plus 1 minus r, which is e sub n plus 1. And all we have left on the right side is 0.5 g double prime of r times the square of e sub n, so that we have e sub n plus 1 behaving like 0.5 g double prime of r times e sub n squared. This means that the Newton-Raphson method or Newton's method converges quadratically or has degree 2 convergence.